Hey everybody. For the next talk in the session, I'd like to introduce Bryan Dury, who will be presenting a QUBO formulation for qubit allocation. Before Brian does start, though, I'd like to mention that at 6 p.m., Ross will be delivering closing remarks on IWQC and also awarding a prize for the best student presentation. I'll probably remind you all about that at the end as well. Anyway, Brian, take it away, please.
All right, thanks so much. All right, so my name is Bryan Dury. I'm a fourth year undergraduate student over at the University of British Columbia, and today I'll be talking to you about the qubit allocation problem. Specifically, I'll be talking about some work we did where we formulated it as a QUBO and then got our allocations out of our cost function using simulated annealing. So let's kind of get straight into it. So the first thing to look at is, well, what is the qubit allocation problem? Well, essentially you have some quantum program, which is giving you some list of operations that are happening to your qubits, and you send that off to some compiler. And the compiler basically gets it ready to run on an actual piece of quantum hardware. And one of the steps the compiler has to do is this step of allocation. So that's what we'll be focusing on here today. It's the step where you're taking the logical or circuit qubits of your program and finding an assignment on the actual hardware graph of your machine. So of course, there's usually further steps of optimization, like, getting your swap gates routed nicely and things like that, but we won't be addressing that here. We'll just be focusing on the allocation problem and trying to find good initial allocations. So now that we know what we're kind of doing, we can kind of ask the next obvious question, well, what is QUBO? Well, QUBO, or the quadratic unconstrained binary optimization problem, is essentially a way of reformulating a problem as an optimization over a set of binary variables, where at the end of the day, you're just trying to find the set of binary variables that minimizes this cost function. So you can see it kind of has this form, it's broken up into several parts. So let's kind of move through this step by step so we can get a good idea about what's going on here. So the first thing to look at are the binary variables. So in this case, they take on one of two values, either 0 and 1. And since we're doing qubit allocation, what the variables represent is whether or not you should make a certain assignment of logical qubits to hardware qubits. At this point, I should mention that the QUBO formalism is mathematically equivalent to the two-dimensional Ising problem. So any familiarity you have with that should apply here in some form. So the next thing to look at are the coefficients in the cost function. So these are really the heart of QUBO at the end of the day. If you look at the Q coefficient, this is in kind of the first term here, which is dubbed the quadratic term. It's dubbed quadratic because of the nature of the interactions of the variable within that term. So what that kind of means is when I say that Q is encoding the quality of the two qubit operations, it's because that term is looking at allocations with respect to other allocations having been made. So that at the end of the day is going to be encapsulating your two qubit operations because you're looking at pairs of allocations. Then if we look at the second term, this is kind of, similarly dubbed the linear term because you're looking at allocations within isolation. And if you're just looking at single qubits, the really the only information you have available to you to assess the quality of them are your single qubit operations. So B is going to end up encoding the quality of those. The last thing to look at are the constraints. Now, I know that it says unconstrained in the name of QUBO, but what that's referring to is that you're not constraining the values that your variables can take on. I mean, they're binary in this case. But of course, if you're going to support general problems with QUBO, there's going to be problems that need certain constraints put into place in order for that problem to actually get physical solutions out at the end of the day. So in the case of qubit allocation, the constraint that we need to enforce is to ensure a one-to-one mapping of logical to physical qubits on your hardware. The reason why that's important is because if we don't ensure this, then we're going to get allocations out that are, having multiple assignments of logical qubits to physical qubits or vice versa. And if you think about that for about 3 seconds, you realize that that doesn't make much sense. You can't have like a physical qubit doing the job of two logical qubits. So we put in these constraints into this form here that I'm kind of mousing over. You can see that we put these funny little coefficients in front. Those are called the penalty coefficients because what these constraints are doing is you're basically adding a term to the model And when you have an allocation that isn't satisfying that term, you're going to incur a cost. And since at the end of the day, you're minimizing this cost function, you're going to be increasing the costs of the allocations that you don't want, the unphysical ones. In general, these coefficients, you can set their value, or the value that you give them kind of sets the penalty that those bad allocations will incur. And in general, you can kind of just set them to large arbitrary values. If you have any more questions on that front, just shoot me one at the end of the talk. So now that we know what QUBO is, we can kind of ask, well, why should we use it? And I can kind of think of three main reasons why QUBO is appealing. The first of which is QUBO is quite flexible. By flexible in this context, I mean that you can kind of put whatever you want to care about for your qubit allocation problem in for the coefficients of the QUBO. And at the end of the day, you're going to get allocations back that do a better job at improving upon the metrics you put in for your coefficients. So let me kind of break down what I just said there. Let's say, for example, you wanted to improve the fidelity or the, use qubits that have lower error rates on your hardware graph. So you improve the overall fidelity of your quantum circuit when you run it on the hardware at the end of the day. All you have to do with QUBO is give some of that information of the fidelities or error rates in for the coefficients, like for the Q term, if you give it some idea of the 2-qubit error rates, or for the B term, the single qubit error rates. The allocations the QUBO spits out at the end of the day, if you look towards the low cost or low energy end of them, they're going to have improved fidelities as compared to not having that information put in for the cost function. So that flexibility really plays at the heart of why QUBO is, a really great tool to use. The second thing that I can think of that makes QUBO appealing to use is that it's circuit agnostic. What I mean by that is it doesn't matter how many gates you shove into your quantum circuit. At the end of the day, QUBO is going to have the same performance. And the reason why that is because QUBO only scales as the number of variables you have in your cost function. And that number is going to scale like the number of circuit qubits multiplied by the number of hardware qubits. At no point do we have gate dependencies that are slipping in here. So we can handle circuits of arbitrary gate count and therefore arbitrary circuit depth, which is quite appealing if you look to compilers like Qiskit, where as you move past the 10,000 gate range, it takes quite a bit of time to optimize those circuits and figure out what's going on. The final thing to think about is the the ability of QUBO to utilize live data. Now, the reason why I feel like this is important is that looking forward, we're going to have access to a lot more calibration data from pieces of quantum hardware or quantum computers that we're running with, and we're going to want to make use of those to improve the compilation process as a whole. And QUBO allows us to do that quite easily on the allocation end of things, because we can really just take this calibration data, like error rates or gate fidelities and things like that, and shove it into the coefficients, and that'll, as I said before, improve on the allocations we get at the end of the day with respect to those metrics. So now we know what QUBO is and why we should use it. We should address the question of like, well, how do we get our allocations from our cost function? So we chose to use simulated annealing. And if we're using simulated annealing, it's actually quite easy to get your allocations at the end of the day. All you have to do is evaluate your coefficients for all of your variables, take your final QUBO cost function and feed it into a piece of simulated annealing software. In our case, we use D-Wave's Neal package, primarily due to the reason that they already support QUBO operations, so it's quite easy to work with. And finally, we get a distribution of allocations back, and you can specify how many allocations you get back. Now, that's an important point to touch on here. By using simulated annealing, we can actually get more than one allocation back instead of just one, like most other contemporary allocation algorithms. So here's a little energy histogram here. Plotted along the x-axis, we have the energy or the cost of the allocations we're getting back. This is for a 1000 anneal run on a 7-qubit circuit from our benchmark set, with a pretty moderate gate size around, as you can see there, around 6,000 or maybe 7,000. So if you look at the shape of this thing, we see a peak kind of in the middle of the distribution, but it looks a bit log normal. And as you pump up this anneal number that you're getting back, it kind of smooths out into this log normal distribution. And actually the shape and size of this distribution is kind of a function of the size of the circuits you're using and how many gates are present in them. So when you have smaller circuits with fewer gates that are pretty easy to explore the possible space of allocations, you'll end up seeing more of a convergence on certain energy levels, and that's kind of indicative of the QUBO method kind of converging on the best possible allocation sort of thing. But this will not be the case as you move to larger circuits and larger hardware graphs, because there's simply too much space available to converge on one single energy. So now that we have an idea of using simulated annealing, we can kind of get at like, well, what are the benefits of using simulated annealing? Of course, I just talked about the fact that we can leverage these distributions of allocations, but let's kind of play with an interesting example here. So what I have shown here is an allocation heat map. So what we've done is we've taken about 50 anneals for an 1,000 anneal run on this circuit specified here, and we've gone to different places in the energy spectrum and taken 50 anneals. So one here, and one here at the low, middle, and high end of the energy distribution. And what we're looking at is, well, where are the qubits being allocated to on the actual hardware graph? So if we look at this for the low energies, we're seeing convergence on a particular place. This is 100% convergence. All of the allocations are going to these 6 qubits as a subset of the hardware graph. I should mention that the hardware graph being used here is IBM Melbourne. It's a 15-qubit hardware graph available from IBM. And also to point out here that the sizes of the nodes and the width of the edges here are indicative of the error rates of those 2-qubit and single qubit interactions on the hardware graph. So bigger is better here in the sense that they're uh, lower error rates. So this node here is one of the best single qubit error rates on the graph available. And you can see that we've kind of converged in some of the best error rates available to us on the hardware graph. Of course, this is quite good, and maybe you could like flip this around and do it here. So it can still get a bit lost in the energy landscape. And you can see as you move to these higher energies, these allocations kind of spread out and explore the space they have available to them. So that's kind of an interesting way that we can leverage simulated annealing to kind of get a better idea about what's happening on the back end of the allocation process. So now that we know kind of the methodology and the methods we employed, let's get at what we actually did. So let's look at our benchmarks. So we worked on 2 set of benchmarks, one of which is that we compared QUBO to the other initial placement methods available in Qiskit and Ticket using around 151 benchmark circuits. And these are the benchmark circuits from the IBM Developer Challenge that were released a few years ago. The second set of benchmarks that we compared QUBO on is that we tested how close QUBO allocations are to the depth optimal allocation or solution using the QUACO benchmarks, which was actually recently talked about in a talk earlier today. And I'll talk about more of that later. So let's focus on the first part here. How did QUBO do compared to other initial allocation methods? So if we look at this table here, what we have is total CNOT count for the final circuit and circuit depth. And what we're taking is a ratio, or what we're looking at is for what percentage of circuits in the benchmark set did the QUBO method yield better results than the given methods? So if we look at pretty much every value we have here, QUBO is doing better for the majority of the benchmark circuits available in terms of total CNOT count and circuit depth, besides one case where it compared to Sabre on CNOT count and kind of lost out by about 1.2%. So what we should mention here is that we're using this particular coefficient form, which we kind of honed in on doing some testing, that we found to produce pretty good allocations with respect to the metrics we cared about, which is swap count and success probability. And we're using the lowest swap QUBO allocation because, of course, at the end of the day, we have thousands of allocations. We have to pick one of them to use to actually compare to the other methods with. So what we're doing here is we're taking that allocation, we're feeding it into Qiskit, and we're feeding it into Ticket, and then we're counting up our total CNOT count and our circuit depth at the end, and then comparing them. So that's where these numbers are coming from. So we can see that it's doing pretty good. But this is kind of like we're zoomed out and we're looking at a macroscopic picture of how QUBO is doing. We're really not getting a sense of how these methods are doing on a circuit by circuit basis in our benchmark set. So let's kind of look a bit further into that. So the way that we're going to look at this is through box plots. I'm not sure if people are familiar with using them before. So this is what the distributions represent on the right hand side here that you can give a look at. And what we're going to plot is as a function of logical qubit number, just as a way of enumerating all of the circuits, we're going to look at the distribution of percent differences with respect to different metrics that we're looking at. So for here, we're looking at circuit depth and we're comparing QUBO and Sabre. So what this means, if we're taking a percentage difference, is we're taking the circuit depth that Sabre gave us and that QUBO gave us, we're taking the difference and then dividing it by QUBO again, so we get a percent difference out at the end of the day. So for numbers below 0 here, that's indicating that QUBO is winning out on the method being portrayed, which is Saber. And if it's above 0, then that means Saber is winning out. So this is how the data is looking. So let's look at a test case of this data to get a better idea of what's going on. So this is Saber again, and we're comparing for total C0 count and circuit depth. And as you can see, there's this little bump in the center where it seems to be pushing in the direction of QUBO doing better, and maybe a bit of bump in the favor of Saber here. But in general, if you kind of look at everything, it's not really clear if there's a winner. You know, if you can say QUBO did better 50% of the time, it's kind of worthless if you don't really know what's going on at a circuit by circuit level. And you can see that these distributions are quite wide in some cases, meaning that, you know, it's on a circuit by circuit basis, it's kind of going back and forth who's doing a better job. And there really needs to be a bit more work done here to kind of categorize, you know, exactly why are certain allocations doing better than other ones, given, you know, the circuit composition or some other variable going on that's deciding the winner at the end of the day. So let's move on to the other thing we did, which is compare using the QUACO set of benchmarks. I know the talk was just given, but I'll briefly explain what they are. So these are the scaling study benchmarks. So they're looking at a larger optimal depth, and the QUACO benchmarks themselves are developed in such a way that you know the optimal depth of your circuits after you produce them. So we can use that to look at kind of debug, like how are these methods doing at finding like the true optimal solution or allocation at the end of the day. So what we've done is we've taken the lowest swap QUBO allocation again after annealing for the QUACO benchmark circuits. And we're looking at, after feeding the QUBO allocations into TCAT and Qiskit for these different hardware graphs, how are the QUBO allocations doing at getting to depth optimal? And you can kind of see this stark this difference between these smaller hardware graphs and these larger hardware graphs. So Rochester and Sycamore are around 53 qubits, and Tokyo and Aspen are around 16 and 20 qubits. So you can see that for the smaller machines, we're getting, you know, pretty decent results, around 2 to 4 times optimality here. This is the depth ratio. So we're just taking the circuit depth that QUBO found and dividing it by the optimal depth. So if we get to here, that would be 1, that would be the perfect case, just to square things up there. So you can see that there's this large difference as we hop up to these 53 qubit machines where we're sitting around the 10 to 14 range. And if you compare between TCAT and Qiskit, it seems Qiskit is doing a bit of a better job with the allocations than TCAT does, but the main effect seems to be this stark contrast between the sizes of the machines, which is kind of muddying out QUBO's ability to find these better allocations. So let's summarize what happened. So what we did, we formulated the qubit allocation problem using QUBO, and we solved the QUBO cost function using simulated annealing. We found that QUBO did better than the other initial allocation methods available in Qiskit and TCAT for the majority of our benchmark circuits, but we found that the best QUBO allocations were quite far from depth optimal. And looking forward, well, how can we improve the allocations for larger hardware by generating more samples, perhaps? That would be something to look at. And maybe to try using specialized tools for simulated annealing to cut down on solution time. At this point, I would like to thank you for listening and ask for any questions.
Hi, Brian. Thanks for an interesting talk. I'd like to remind everybody now that we will be taking questions in the Dury de Matteo Slack channel. I do have a question in currently, which is, Brian, could you go back to your first benchmark slide, please?
This guy?
Yeah, that one. I was just wondering. I don't think you mentioned what software you used to actually route the QUBO initial placements you found to derive the number of CX gates ultimately needed for routing.
Right. So the numbers that are being shown here is after we wanted a fair comparison, right? So the placement methods here in Ticket, and then these are in Qiskit, the trivial to Saber methods. So what we're doing is we're finding our QUBO allocations using simulated annealing, which is using D-Wave stuff. And then we're taking that allocation and we're giving it as the initial allocation to Qiskit and Ticket's compilers. And then we're using the tools available in there to count up total C0 counts and circuit depths.
Okay, so for the line placement and graph placement case, you've passed the QUBO allocation to Ticket's routing method, and for the other 4 to Qiskit's.
Mm-hmm.
Okay. Out of interest, for the routing you did with Ticket, just because I'm involved with it, what parameters did you use for the actual solutions you found?
Yeah, so this is an important point. Since we're trying to compare just how the initial allocation methods are doing, we tried to turn off all possible optimization we had to just really focus in on how the initial placements are doing. So in Ticket, I think you have things like the bridge gate parameter and swap look ahead and things like that. So we basically took all of those and we put them to 0, just so it's just doing the most basic routing it can to try to get the initial allocations being compared on some fair playground.
Okay. I've got a final question. I should probably just check the Slack channel. Which is that when you, I'm going to use the word cost, it might be ineffective, but when you cost your allocations found during the simulated annealing process, I assume you find some initial allocation, you have to in some way decide how effective it will be. Do you, I guess, emulate the number of swaps you'd expect to be introduced? I was wondering how you do that.
Yeah, so we employed kind of this naive swap count to kind of see how the different allocations are doing. Where we don't have any like fancy routing we do. We basically take all our allocations and we ask like, okay, given this initial allocation, going through the circuits we're looking at, say there's a C naught count or a C naught gate that can't be realized, we basically just swap it into place so that you can perform that C naught operation and then immediately swap back. So there's no like, it's not really an optimized routing process, but it kind of gives you like a general estimate of like, well, how many swaps will it take for this initial allocation? So that's what we used on our end to kind of score the different things.
Did you ever compare that to actually routing these circuits and seeing how often it accurately predicted which
Yes. Yeah,
okay.
so this is actually a really interesting result that I'll maybe just like briefly talk about. But if you look at the QUBO end of things and you ask like how correlated are the lower swaps to the lower energy allocations, you see a pretty strong correlation. But when you take all of those allocations and you feed them into another compiler like Qiskit and Ticket, you actually see that the correlation starts to like die off and it becomes more clouded sort of thing. So it really doesn't you really kind of lose out on your predictive power of how are these allocations going to do at the end of the day after you run them through these compilers that are available.
Thanks. That is an interesting comment. Um, I do have one final question, and I'm assuming have you run any of these circuits to an actual device? Because I'm just wondering, in your cost function, you introduced error rates, and I was wondering like how often, like how helpful that was for actually predicting which placements would introduce the least error during actual running on devices.
Yeah, so
But
we haven't run anything here on actual devices, but on the back end, kind of what I was saying with swap count, we did a similar thing and we calculated success probabilities of our circuits. And if you took the same allocations that you say were like the best success probabilities you found for running the circuit, and you fed that through compiler, you again kind of lose this correlation with are these high success probability circuits that we calculate on our end using our naive swap count, are they going to be predictors of the compiled circuit at the end of the day running on real hardware that's going to do the best job? And it's not really clear that they are going to be. But that I say that you lose this correlation, there's still kind of a correlation. Like
Mhm.
on the lower energy side, it's still like kind of a predictor, but it's not as strong as you'd like it to be.
Okay, thanks for that. That's interesting to hear. I think then it looks like there are no questions in the Slack channel, so I think we'll wrap this up here. I'd like to remind everybody again that at 6 p.m. Ross will be giving closing remarks on the conference, and there is a link to that in the During Di Matteo Slack channel.